What's up, everybody? Today on Universal Theory, we're going to be talking about the Copenhagen Interpretation versus the Everett Interpretation. If you haven't heard of either of those, stick around and you'll know both of them in the next 10 minutes. Hopefully you like the new format. If you do like the new format, let us know in the comments down below. We are still going to do long forms. We actually have a couple interviews lined up, and they are extremely exciting, the interviews that we have lined up. I don't want to give anything away yet. You just got to stay tuned to find out. But let's just say that we are growing and people are noticing and people are wanting to, they're doing us favors, but they see what's happening over here, and that's because of you guys. So thank you so much for all of your support. Now into the Copenhagen and Everett interpretation. The Copenhagen interpretation is this wave function that we've talked about. That this idea that the particle exists in a state of potential when we haven't measured it. That is what's happening in the Copenhagen at the beginning with the Copenhagen interpretation. And in that sense, it's kind of similar to the Everett, but different. We'll get to that. So, right, it's one electron existing in a superposition. So it's one electron existing in multiple states. And then when we measure it, not necessarily observe it, but measure it, it collapses. And now the totality of that wave, of all that superposition, has collapsed to one particle. Okay? Now, that works in a lot of ways. There's a lot of ways that it works. The reason why it has the name Copenhagen interpretation is Einstein and Niels Bohr had a famous debate. And if you aren't familiar with Niels Bohr, he was a renowned physicist at the same time as Einstein, and they actually have something called the Bohr model of the hydrogen atom. So he was very instrumental in understanding the subatomic world or the atomic world. So that's why it's called Copenhagen, because it's some city. Copenhagen is the city in which this debate happened, and Niels Bohr arguably won that debate, and that's why it has the name Copenhagen. So there's a little factoid for you. And as we kind of have advanced through society and computers have gotten better, and I think it was it was like 50 years later, we had this guy named Hugh Everett. And Hugh Everett was another physicist who said, hey, the math is right. Why are we messing with it? We know the math is right. It's been right for the past, 50 years. But he didn't feel right about this collapse. The idea that, it's one electron in a state of potential interfering with itself. He said, what if each probability corresponds to an electron? So let's just say that we have a wave function where when it's squared, that's how you get the amplitude, where there's 4 possibilities. He's saying there's 4 electrons, and those 4 electrons exist in 4 different universes. And when they're moving through space, they're interfering with each other's space-time. They're literally moving each other's space-time, and they're affecting each other as they pertain to this and that and that and that universe. And then when we observe this wave function of the 4 electrons, one of them is for our universe, right? Because we know it collapses to 1. So that one that is a part of our universe will decohere from that wave function that it's existing in, and it'll now just exist in our universe. It no longer is affecting the other universes. Let me say this. The other electrons are no longer affecting ours. I can't speak to if it collapses in these parallel universes, but we do know that the electrons from the other universes no longer affect ours. So I don't know what makes more sense to you, what's more intuitive to you, but to me, that is much more intuitive. But I also contemplate on the multiverse on kind of a daily basis. Yeah. So, and I know you do too, right?
Yeah,
so.
I kind of think in multiverses.
Yeah.
I enjoy the Everett interpretation. We talked about conservation before, and then me and you talked about the concept of conservation in the Everett interpretation, where he's saying that once this entanglement happens through an observation of a quantum system with our universe and our classical systems, once the electron has been observed whether it be us or a machine or another atom or a particle or whatever, once it's observed, it decoheres, like he said, from the other electrons in the other universes. And now there's a specific occurrence that happens in this specific universe, and then there's a branching effect where these other universes come into existence. But then, within his theory is conservation. You have to have conservation. So in his theory, energy is conserved in these other universes. If you're wondering that, because you say, where if energy is conserved, where's this? Where does this energy go or come from for these other universes to come into existence? Well, the question is, where? You know, and does it split our universe in half? And do we lose half of our energy and so forth? So in the theory, they say no, it doesn't do that. It does share energy with these other universes, but it causes a thinning. So it's not it's not half of a thin or a quarter of a thin. It's very minute. But I couldn't tell you exactly what it is because I don't study the math, but I'm just familiar with the theory.
You're right.
But me and him had talked about this, and I had always thought about it before I was familiar with the Everett interpretation. I always thought about how, if hypothetically, imagine if a Big Bang happens and then there are, let's say there's 4 universes. Like you said, there's 4 possibilities of this electron. So there's 4 universes. And then they're all deterministic because they're all on a causal relationship with each other. So once one makes an observation, all of the other 3 were simultaneously making their observations, and they were deterministically making the only observation that they could have made based upon the causal relationship of the Big Bang and the trajectory of the unfoldment of that particular universe in parallel to the other universes. Now, there could still be a branching in each universe where you could have parallel universes happening simultaneously and they're all being deterministic, and then you could have another deterministic facet of each universe where there is a branching and there is a thinning. I'm not sure. I'm not a physicist, and I'm not as well versed with the math as much as Trent is. Maybe he can speak on it, but that's the thing about the multiverse is we don't actually know how it works.
Yeah. We just know that the math says that it's true. And as Jordan was talking about the cause and effect relationships from the Big Bang all the way through, that's something that a physicist thought as well. And I can't remember who it was Laplace's demon. I think it was, actually he's a mathematician, and most mathematicians are physicists as well, unless they're pure mathematics. But Laplace's demon was saying if you could keep track of all the information everywhere, you would always know what was happening and what would happen next and what would happen next and what would happen next because of the causal relationships.